All right, so we have a simple definition of aromaticity versus anti-aromaticity, right? And we have aromatic systems are very stable, anti-aromatic systems are very unstable. This is pretty easy when we have nothing but pi bonds to worry about, right? We can just count up the pi bonds, multiply by 2, see if that number is divisible by 4, and that tells us, is this compound aromatic or is it anti-aromatic, right? And so we'll do a couple of examples of that, but we're also going to look at charge, right? Sometimes there will be cations or anions, and sometimes there will be heteroatoms. And so we're going to have rules to kind of deal with all of those things. Remember throughout all of this that the thing that we're looking for is that aromaticity means that a compound is stable. Anti-aromaticity means that a compound is very unstable, right? And then non-aromaticity is somewhere in between. That's when we don't have either of those things. All right. So if I give you a very large ring, right, and we put a conjugated system throughout, right? So double bonds, every carbon is going to be part of a double bond here, right? If I ask you, is this compound aromatic or non-aromatic, you would go through and say, okay, I've got 1, 2, 3, 4, 5, 6, 7 pi bonds. That's 14 pi electrons, right? We have a complete cyclic conjugated system. So we have a complete system, and by that I mean no sp3 carbons. Okay. We have a complete cyclic conjugated system. We have 14 pi electrons, which is not divisible by 4. And so all of this comes together to tell us that this is aromatic, right? And stable. We can go very simple, right? I can give you a 4-membered ring. This is a conjugated system. It's cyclic. There are no sp3 carbons in it. So we can, first of all, we have a complete cyclic conjugated system. Oops. Right. And we have 2 pi bonds. That's 4 pi electrons. 4 is divisible by 4. This would be anti-aromatic. Right. And so cyclobutadiene is actually a very, very unstable compound. And so this kind of thing is pretty easy. Can we count the number of pi bonds in a molecule? Can we make sure that we don't have a neutral sp3 carbon in our molecule, etc., etc., right? So let's do, let's see if I can find an example here. Let's do, so is this an aromatic or anti-aromatic system? You would look at this and you would say, all right, so I'm looking at my pi bonds, and right here, I have a neutral sp3 carbon. And so it doesn't matter how many pi bonds I've got. It doesn't matter if the number of pi electrons is divisible by 4 or not. This doesn't have any aromaticity. So this is a non-aromatic compound. And so we don't have to worry about the number of electrons that are in it or not. This is just kind of in that in-between stage. It's less stable than an aromatic system, but it's more stable than an anti-aromatic system because it's still conjugated, right? So now if we were to try to do any reaction with this, we would have to worry about, well, I guess we have 10 electrons here, so you could do 1,2 addition, 1,4 addition, 1,6, 1,8, or 1,10 addition, right? So you'd have a lot of possibilities. But the trick here is observing this neutral sp3 carbon. There's a carbon in there that doesn't have a pi bond associated with it. And so that's going to break the cyclic system. Now, what happens with charge, right? So charge can also, right, because charge participates in resonance, charge is part of resonance. And so charge can complete a cyclic conjugated system. So charge can be part of a cyclic conjugated system. So if we have a 5-membered ring, we can actually make systems that are aromatic and or anti-aromatic, right? So let's look at 3 different 5-membered rings. This one's going to have a positive charge at that carbon. This one's going to have a negative charge, right? And this one has neutral. So first of all, this one's pretty easy. We have a neutral sp3 carbon right here. And so this is going to be non-aromatic. Okay? So this will be, again, less stable than an aromatic system, but more stable than an anti-aromatic system. In both cases, we have 2 pi bonds. These two have complete circuits, right? So these have complete cyclic conjugated systems. We have our conjugated system of pi bonds, 1, 2, 3, 4, and then we have a charge here. And so the reason that we can think about these as completed conjugated systems is think about the resonance, right? So if I draw, I'm going to label these carbons. So this is carbon 1, 2, 3, 4, 5. Carbon 1 can easily can have a pi bond associated with it if we draw the resonance form here, where I move that pi bond over. I do this, right? So, and then I can keep doing this, right? I can move this pi bond over, and so every carbon in this molecule will have a little bit of positive charge associated with it, but also every carbon will be part of a pi bond. So that means that the cyclic conjugated system is still complete. And so we can say this has a complete cyclic conjugated system, right, with resonance. We have 2 pi bonds, and that equals 4 pi electrons, and we have a cation. Now the cation has no electrons associated with it because it's positively charged, so there's no pi electrons associated with that cation. And so total, we add these up, we've got 4 pi electrons. 4 is divisible by 4. This compound is anti-aromatic, right? Because it's divisible by 4. We have a complete system, a complete conjugated system that's cyclic, but we have the wrong number of electrons. We have a bad number of electrons. We have 4 pi electrons, right? So let's look at what happens over here. Now, a negative charge is just a lone pair, right? So that equals 2 pi electrons. And so we call those pi electrons because, of course, in resonance, we use that lone pair to make a pi bond and then create a different lone pair over here. And so those electrons that are in that lone pair are still going to count as pi electrons. Keep going, right? And so what that means is that we're going to have a different number of pi electrons in this structure than we did in the previous one. Right? So again, we have 2 pi bonds, 4 pi electrons, plus we have a lone pair, that negative charge, so that's going to be 2 pi electrons. Add those up, we get 6 pi electrons, and we get, that's not divisible by 4, and so this compound is aromatic. And so depending on the charge that we have for this molecule, we may have an aromatic compound or we may have an anti-aromatic compound. right? The important takeaway message from this slide is that charge still completes a cyclic conjugated system. Right? So if we went back to our structure over here, right? This structure that has a neutral sp3 carbon, this is non-aromatic, but if I put a lone pair at that position, now I have to redraw it, which was a mistake. If I put a lone pair at this position and make this a negative charge, now every carbon on here has some pi electrons, right? They're either part of a pi bond or it has charge. Now we can start to look at, is this compound aromatic or anti-aromatic? And so we have 5 pi bonds. So this is going to have, that's 10 pi electrons plus the 2 pi electrons from the lone pair, 12 pi electrons. This is anti-aromatic. And so making this compound would actually be very hard to do because it would be so incredibly unstable. So putting a negative charge on here is easy to do on paper. In practice, we would probably not be able to make this compound because it would end up being anti-aromatic. It would be very unstable and it would react very quickly to become something else. Right? So, but you can think about what would happen if we put a cation here, right? Then we'd have 10 pi electrons and we'd have an aromatic system. So making the cation is going to be much, much easier than making the anion.